I wanted to finish up the discussion in this chapter with a very specific type of problem. Normally we would have done a similar laboratory kind of experiment with this, but I don't think I'm going to try to do this particular experiment with our online classes. But in any case, it concerns something called a ballistic pendulum, and a ballistic pendulum is something that you can use to measure the speed of something that's really fast, like a bullet. So the idea is, if I want to measure how fast a bullet is as it leaves a rifle, it's moving so fast that, at least in the old days, before the days of high-speed photography, it would be really difficult to measure its speed directly. So instead we're going to do it indirectly. What you do is fire the bullet into a block of wood that's suspended from the ceiling or something above it like this. So you've got these two strings hanging down. Here's a block of wood, and you make sure the wood block is big enough that the bullet gets embedded in it. In other words, in that collision between little m and big M, the piece of wood, it's completely inelastic. We're going to make the two stick together in the final state and move as a unit in the final state. So here's what they look like before. And then after these two have this very quick collision, they combine into a single object of mass little m plus big M. Then, of course, that combined mass is going to be moving to the right just after the collision. And what it does is rock up to a certain angle. In other words, there's a certain change in height of this block. And the idea is, if you're clever enough and you are able to use energy methods and the conservation of momentum, by measuring how high this block rocks up, you can infer what the initial speed of the bullet is. Now, I'm not going to solve this particular exact problem here, but rather I'm going to use it to help advise you on how to solve a related problem that's in the homework on Chapter 7. So let's go to that problem. Here's my version of the problem. Problem 13 has 3 parts, and it's somewhat like the ballistic pendulum, except in this case we have 2 small spheres, and they're suspended from the same point by strings of the same length. Okay, so one of them is just at rest, sitting at the bottom. They have unequal masses, but the strings are the same length. We pull one up to a given angle relative to the vertical, so I pull the initial one up to an angle of 68 degrees relative to the one that's hanging straight down and is at rest, and I let go of the one, releasing it from rest at the position shown up here. First part asks, with what speed will the lighter mass hit the heavier mass? In other words, when this one gets right down here and it's just about to strike the heavier one, what's its speed just before that collision? And the way we're going to answer this is, one way to think about it is it's very similar to that. We did a problem that involved an ice cube sliding down a hemispherical bowl. Notice that this mass is it's as if it's sliding down a hemisphere here, and it's as if there's no friction happening, and the string force in this case is acting just like the normal force did in the hemispherical bowl. So it's very similar to that one. And we're going to apply the same approach. We will take our system to be, we're not really involving in this first part the second mass. We're only going to consider the first mass. The initial is up here, and final is just before striking the other one when it's down at the bottom. So our system will take to be the smaller mass plus Earth, and we'll take gravity to be an internal force, but we'll take the string tension force on one moving part of our system to be an external force. We don't really care about it because it's not doing any work. It's always pulling in the direction that is in the direction perpendicular to the direction it's going at every moment in time. So let's apply our old friend. The net work done by external forces to the system equals delta Ke plus delta Pe. In this case, the only external force, if we're ignoring air resistance, that seems reasonable here, the only external force that might have done work is the string tension on moving parts of the system, and the string tension does 0 work on it as it goes from the initial to the final state, because the string tension is always pulling on the ball that's moving in the direction perpendicular to its motion at every instant in time. Okay, change in kinetic energy is the difference in 1/2 mv squareds. Change in potential energy is the change in mgy. So let's take some conventions. When we use mgy, we have to take plus y is up. If we're going to use that potential energy form, we'll take the initial to be the release, final is just before hitting the other one, and the work done by tension is, the tension force is 0 because it's perpendicular to the direction of motion. So let's plug those things in here. The net work done by external forces then is 0. The initial kinetic energy is 0 because it's not moving initially. And we've got to figure out what y final minus y initial is. My goal is to figure out what v final is, solve for it, but we've got to first figure out what y final minus y initial is. We'll eventually cancel those m's there too. We could divide by m at this point. But y final minus y initial is, well, first of all, it's negative. If plus y is up, and we have to use plus y is up if we're using mgy as the potential energy, then this change in y is negative. We're going down as time goes on. So y final minus y initial should be some negative number. How far does it go down? Well, I can figure out, I've drawn a little horizontal line here, and that makes a right triangle here. We know the hypotenuse length, so we can figure out the vertical side of this right triangle because this angle is 68 degrees, and that is going to be 10.5 meters times the cosine of 68 degrees is just this part. That's not what we're interested in. We're interested in this part, but it's also true that the string length is 10.5 meters, so this is 10.5. So if we do 10.5 minus the 10.5 times the cosine of 68, we get what's left over down here, and that means that's what the change in y is. First of all, it's a negative change in y, and the magnitude of change in y is that difference I talked about there. We got to put the extra minus sign in front of it because it's going down in potential energy. So in other words, it's going down in y from initial to final, so we got to make sure it's a negative quantity. All right, I've canceled the m's in this case down here, and now I'm just going to solve for v final and plug these numbers into my calculator, and you get the final speed of this smaller mass just before it strikes the larger one is 11.34 meters per second. Part 2, what's the speed of the combined system just after the collision? So the two have a very quick collision. They stick together in the final state. Maybe they're covered in Velcro or something like that. What's the final speed of the combined pair just after the collision? Not in this picture that I'm showing here, but right when they're essentially still vertical, still right at the bottom, but they're moving to the right. How would we figure that out? Well, momentum is conserved in that very quick collision. It's an inelastic collision. Kinetic energy is not conserved, but momentum is conserved. And that's because, well, you know, there are collision forces between the two. The only other forces that are acting on these in the short amount of time where the collision takes place are the string forces on them and the weight forces, and they don't even involve impulse components along the x direction. They involve it along the y direction, so they wouldn't come in anyway. So momentum is certainly conserved. So we're going to take initial to be just before, final to be just after the collision, not what's pictured here, but when they're still vertical, but both are moving to the right, and apply the conservation of momentum x components if plus x is to the right. Plug in the numbers we know. In the final state, they're moving as a unit, so there's only one object. Here's the total m, and here's the unknown v final, and we can solve for v final, 4.73 meters per second in my version of the problem. Finally, part 3, what is the maximum angle of deflection of the two bound objects? Answer in units of degrees. So how big is this angle? In other words, if they've rocked up to the point where they come to rest there, just like the ballistic pendulum rocks up to coming to rest, what's this final angle? And in this case, going from just after the collision up to there, it's again like that ice cube sliding in the hemispherical bowl. So mechanical energy is conserved there if we take the right system. So I'm going to take the system to be the combined mass object plus the Earth. We'll take gravity to be internal, but again, the tension force external, and the tension force doesn't do any work, and apply this work-energy relation that we've used so many times. The net work done by the tension going from initial to final is 0, again, because it's perpendicular to the direction it's moving at every instant in time. And we can figure out then, if we wanted to, after canceling the m's, given that we know what v initial is, our initial speed here is the same as the final speed from the previous part. So we know everything except y final minus y initial. We could solve for y final minus y initial, but that's not what we're asked for. In this case, I'd rather express y final minus y initial in terms of theta and just solve for theta. So again, this length of the string is 10.5 here, and after it's rocked up to a final angle theta final, this vertical distance here is 10.5 times the cosine of theta. So if I take 10.5 minus 10.5 times the cosine of theta, that's equal to this change in the y-coordinate there, the difference between those two. So I'm just going to replace the change in the y-coordinate with that difference. And now theta final is the thing I want to solve for. I've canceled my m, I plugged in the v initial into the square there, and we're just going to solve for theta final to do that. Okay, so I factor out the 10.5, solve for the cosine of theta final, and then take the inverse cosine. And for my numbers, I get 26.9 degrees. So that's how to do that homework problem. That's one of the most difficult ones on this selection of homework problems. I hope that helps. See you in the next chapter.